Yeah, another draft physics video presentation. Should be working. Anyway, hi. So something completely different today, maybe. Who knows? I'll try to do an overview connected to other statements and conversations that just seem a little tiny bit related. So first, simple question, so simple answer. Are there experimental data that prove the speed of gravity is of light? I would say the most convincing argument is when they took all the observations that they took of Venus and Pluto and whatever, all the motion of the planets. So if they took all the observational data and they reinterpreted it based on speed to gravity, Newton's equations got better. So the answer they got to the question of where will they be in the future, the predictions got better when they took the observed positions and accounted for the speed of light, the speed of gravity. So that to me would be the most convincing. Now, of course, they have a bunch of these fancy, impossible to understand, idiotic experiments. You could say LIGO, okay, the fraud LIGO proves gravity moves the same speed as light. But I'm going to argue that's clearly a shitty proof. But there's some better than others, blah, 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 blah. Don't know what to say. I mean, from my perspective, it's just as a point of unification, I see no reason to make a force that moves some other speed. And instantaneous, it just seems, if it was such a thing as an instantaneous in the universe, that even stuff like biological matter would figure out how to take advantage of it. We'd have gravity sensors, instead of eyes, because it'd be a huge advantage in being able to instantaneously communicate with things' position. Something like that. The world wouldn't look the way it looks, frankly, if gravity was instantaneous. But anyway, believe what you wish. I would argue that the fact that Newton's equations get better kind of proves it. Proves it well enough for me, personally. And like I said, it lacks continuity to create different forces in the universe. Force is an idea, and it doesn't need more than one answer. Frankly, more than one elemental answer. Obviously, I'm advocating for two varieties of force in the universe, but that's just to create the idea of plus and minus. But it relates to this wind argument. So I did state in the other video about how you can't make something going faster because the wind is only going a certain speed. But there is a trick, right? The trick is you can have wind blow from the sides and keep pushing you faster. That's sort of what's happening in the real physics, coincidentally. I used wind as a metaphor for a video I did on economics. Frankly, the comment doesn't belong here. I'm almost tempted to answer the question. Yes, they're going to borrow another 1.5 trillion by putting in the FDI, the Fed's reserve accounts. So they're going to tell the banks to go buy bonds off the market, use one of their checks, and the check will never be cashed. The check will come back to the Fed, essentially, where all the checks come back to get paid, and all they'll do is increase the bank's reserve number, saying that basically we owe you $1.5 trillion in cash. So it's like the banks have their vault in the Fed, and what you're really just doing is you're pretending the bank took money out of its vault, and where it put it in the Fed. So the Fed just gives them more credit, so that bank ends up with more credit. Now, it's not real credit because we're sort of making a deal saying, be quiet about this, okay? We're really just borrowing the money. So it's just $1.5 trillion more of debt, period. It's nothing else. It's a liability for the federal government to have to pay the banks the money, put it back in their vault. We owe their vault $1.5 trillion. That's simple. Just absolute bullshit. Completely. See, what we're buying is we're buying our debts. So we're going out into the market and saying, do you have one of our IOUs? Yes, we'd like to buy it off the market. See, because every time you buy something off the market, right? No matter what it is. You buy a big pile of corn, you buy a big pile of oil, you buy anything. When you take it off the market, that means the rest of the oil or the rest of the stuff gets more valuable. And because all these commodities are in one market, it makes the market more valuable. It's like buying paintings, right? The fewer paintings there are, the more value they have. The more paintings there are, the less value they have. So if you can somehow engineer a way to take stuff off the market, make it just disappear, make it unpurchasable, then you made the stuff that's left more purchasable. This is all so simple. It's nothing complicated. So look, this whole economic thing, yeah, it'll work until it stops working. And so all you're really doing is saying how much momentum are you going to pile up, and you could call debt momentum, when you're going to hit the wall. And how big a mess is it going to make? Is it a mess you can clean up, or are we going to turn into like little tiny atoms? We're going to be so vaporized by the crash. And that's all you're doing. You always have to pay debt back. Credit cards are a pain in the ass, right? But you spend on it, and then you got to pay it back, and you spend on it, and you got to pay it back. So there's this terrible negative wind that blows when you have to pay it back. And all the government's doing is pretending, right, like some fucking idiot, I'll just get another credit card. I'll just get another credit card. And these idiots are thinking that's going to work, that you can just keep doing that forever. No problem. Nobody's going to figure out you didn't earn any money, you don't have any money, this is all fake wealth. Nobody's going to figure it out. Well, the reality is going to hit them in the face, and so all we're doing is saying, once the crash gets bad, we're just saying, who cares how bad it is, right? Cancer's cancer, I don't care, it just doesn't matter. You might as well, if it's going to kill me anyway, fuck it. So that's all they're really saying, is fuck it. Let's make as big a mess as possible, because it just doesn't matter. Any mess is a mess. It's sort of true. You can break a piece of glass, and it's kind of just doesn't matter whether it's a big break or a little break. Broken glass is broken glass. You got to replace it, blah, blah, blah. So that's all, behind any of this, is they're just not calculating that it really will make a difference in terms of how you can put it back together, how you can get us floating again once the boat starts sinking. And the truth is they're making it impossible to recover. Everybody's going to have to swim for shore, and the sneaky and the tricky, and the ones who climb over the other swimmers, are going to be the ones who survive, and it's just going to be ugly as fuck. But anyway, wrong subject. Why did you post here? I don't understand. I don't understand you people. So I'll delete that just because, it's not even close. So anyway, wind. All right, so there's... well, the other thing to point out, I guess, while I have this open, I might as well point it out. I mean, you do a search on physics, right, to see what's up today in physics, or this week, or this month, and all you get is a ton of this crap video game shit called physics, Spider-Man, masturbating or whatever. I mean, and all this Hindi stuff, and I got nothing against foreigners, personally, but I just mean they should have a way to filter this stuff. I mean, I don't want to click on a video that I can't understand, but it's amazing that there's just nothing in English. I mean, nothing. I mean, like 3% of these videos. I'm in America doing a Google search, a YouTube search, and 3% of the videos are English. I mean, it's that bad. I mean, it's really that bad. And I can understand. So apparently they have some kind of test there where if you can pass this physics test, then you get a real life. You get to go to university, you get to do this and that and whatever. Something like that anyway. So they just have 15 million videos all teaching exactly the same math. It's all just math. There's no conceptual physics involved at all. So it's just for passing a specific test, and they just have a bunch of... I mean, there is one chick that's really quite, all her cylinders are working. I mean, she's got the look and the brain. But anyway, the rest of them are just kind of, not terribly fascinated, but they all think they're like, well, I'm Butch, I'm cool. I have master physics. I have power physics. I have blah blah blah. You know, it's pretty lame. But I mean, it just goes on and 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 on. You know, just complaining. I just think there ought to be. So I mean, like I said, it's nothing against foreigners, but what the fuck's the point of this? I can't. You know, I have to filter through all these videos to figure out which one is English. And all these foreign ones have English titles, a lot of them, and you're like, you know, they're just deceptive. And even when they speak English, you know, frankly, some of them speak it so badly that there's just no frickin' way to understand anything they're saying. Well, anyway, just a complaint, just an observation. Life seems kind of a pain in the ass that things don't work better than that. Of course, the cowardly old mystic wouldn't, you know, shit for brain mystic was, you know, is ignoring my response videos. But whatever. Can't do anything about cowardice. It's all over the place. So, on to business. Maybe I'll make this a little bigger because I guess I'll just draw crap. Yeah, that's what I'll do. Something like that. No, I don't want to do that. Alright. So I would argue that the universe is just made of the simple things, right? So we have the simple thing of two objects, and we have gravity, right? So the idea that they move towards each other. All right, simple kind of thing. And then we have charges. Okay, we have these two elements, electron and the proton, and they do this inverse thing, okay, where the protons repel protons and they attract in this special circumstance when they're opposite. So when they're the same, they repel, and when they're opposites, they attract. So I guess I could draw this third thing here and just point out that this is just repulsion. I mean, it's, draw it backwards, Gary. They both, yeah, I don't even know how to draw it. Okay, so I'll draw it this way. They repel each other. All right, and then you have attraction this way. And the green thing does the opposite, obviously. So you have this new function of repulsion. And then you have this third thing, the motor force, where these things are involved. And the idea is that the electron can be moving this way. All right, and then you have a force going in and out of the board, let's say, or yeah, we'll do in and out. So I apply a force going this way across it, in the sense that I have the north end of a magnet here and the south end over there, and so I have a force going through it, and it really doesn't have a direction. It's just two opposite forces inversely applied. So the green thing is over here, and the blue thing and the white thing is over there. You know, so it clearly is two opposite forces oppositely transposed. And what that means is, you know, what causes, they're going to have an opposite reaction, right? The force is going this way, and they're going to oppositely react to that direction, in the sense that one is facing it left right, one of them's facing it right left, and so they're going to react oppositely. But then they're also inverted. Okay, so what's going to happen is you're going to get a third force, okay, that's going to drive them up. So instead of just having attraction and repulsion, you have this third thing where it pops out in the third dimension, okay, and the force, the movement goes this way. The trick would be is that there would be stuff coming back in, okay, from the third dimension, and it's going to cause motion this way. So this is sort of like the boat sail argument. So you can sail a boat by just having wind, okay, hit your sail flat, nice and simple. Or I guess I should draw it as a square or something. And then you can angle the sail. So I could make a sail that's like shaped, okay. And now I can blow wind this way and make the boat go this way. I can hit the side of the sail, and that'll give me a third. That'll change the direction of the motion of the force. So we know the force is going this way of the wind because I have the sail angled at that wind, I'll end up converting this energy into energy going this way. All right, and so that's sort of that's the key to this whole function, is the fact that there's part of this mechanism is diverting a force. Now, I would argue the simple explanation is the diversion happens with these opposite forces. So when the white force hits the electron, it diverts it, and when the electron force hits the proton, it diverts it, and that creates your low pressure between them, and that creates your attraction. So it's fundamentally dependent on taking a force that's going one way, not allowing it to get where it's going. This force doesn't get where it's going. The wind is stopped. I mean, this is how, they do this in boat races, right? The two boats will try to position themselves so the one boat wipes out the wind for the other boat, just knocks it out. So it can't do this thing. It can't do this conversion anymore because it's not getting any wind going sideways to increase its velocity. All right, so that's the basic elements. So do I want to get into the drag argument and all of that? All right, well, maybe I'll take a break and then I can think about what arguments I want to get into. Yeah, I'm back. Still really haven't decided where I'm going, but I guess I'll just make this clear again. So I start with gravity. Now, people think gravity is the most elemental force because it's so simple. It's just doing one thing. But the trick is that gravity really is a complication, a consequence of this fact that these charged elements are doing this little thing where they're bending energy, right? Now the trick is, if I took these dipoles, right, you could argue these dipoles are bending energy, right? I mean, energy comes in one way and it comes out another way. And if you put a bunch of them in a row, you could see that all this green stuff would end up coming out this way, right, eventually, and all the white stuff would end up coming out. Well, let's try yellow instead. Yeah, okay, all the white stuff would end up coming out this way over time. It would just be, that's enough of a contrast. And so one side would be all these arrows, and one side would be all these arrows. Now, if I mix them, though, right, if I mix these up in these poles, and I have them going in all kinds of angles or directions, they're facing each other in all kinds of ways. So at every angle, they're at this angle, they're at this angle, they're at this angle, they're all at different kinds of angles. Well, then you could figure out that it's completely neutralized as a filter. It's not segregating anymore. It's creating as much of this over there as it is over here, and it's just creating it back to mixed. So you could say, if I was using some other colors, red and blue, you could say it would just all be turned to purple again. And so you've neutralized one portion of the function of the charges, but the charges still exist in the sense that the charges are still absorbing energy, okay, in terms of that's how they move. They don't move until something hits them, makes them move. And the gravity thing is just happening because when you have one of these things that isn't a magnet, it's just matter, and its poles aren't lined up in any way, so it doesn't filter very well. Like the Earth has a tiny magnetic field based on its mass. Then, okay, you'll end up with gravity because all you'll be doing is absorbing motion. And you're going to absorb it in all the directions, okay, so because the force is hitting you from all directions essentially. Once you have stuff moving inside of you, it keeps absorbing energy, and it's absorbing it in all directions, and that means that from every position on the surface, it's going to appear like there's more stuff hitting you from the outside than it's hitting you from the inside, because you've absorbed energy that was going this way. So you had two arrows here, the equal amount of force on either side, but one of these arrows got absorbed going this way, so it didn't make it to this surface. And that's your inequity that pushes you in. There's less force coming out of the Earth than it's going into the Earth at any one moment. Alright, that's probably enough for that. But it really gets complicated in the sense that you have to understand that all movement is an absorption. So the trick is, okay, is that even when something moves from here to here, it can't be just hit by one little bit. The one little bit just moves it, it goes to here, and then it could give back the one little bit in this direction. That won't work. It actually has to be pushed all the way. All the way, all the way. Every one of these movements has to be absorbing energy from the field, from the stuff that was going this way. So it's converting more little arrows going this way, absorbing them, then it's absorbing the ones coming the opposite way. Now that's intuitively insane. I mean, the thing is going that way. You're saying it should be absorbing more arrows this way than it is this way. So there has to be a mechanism you can make, some arrangement of the sails to make this work. So now you're sort of talking about the complex sailing, where you can actually sail, into an opposing wind, by tacking, and you just keep switching to keep making the the wind coming at you a wind coming from the side. So by tacking, you can create a side wind that you can gain velocity from all the time, and you just use your velocity to keep bending this curve a little, and then you have to tack the other way, and then tack, and then tack. But you can gain forward motion against the wind because you're tricking the wind. You're turning the wind against you into a wind sideways to you. And so matter somehow has to create the same illusion, okay, that when you hit this thing that might be a little bit complicated, have more than one piece to it, and the way they're interacting, the way they're moving the force, means that they're doing the same thing. This thing is causing it to tack, constantly change, so it can absorb more energy going this way than it will interact with coming this way. So it will negate this wind and absorb this wind by turning its sails, and tricking the wind into keeping it moving in one direction. All right, and that would overcome drag. So somebody 1,000 years ago to say you can't sail against the wind, it's not possible, blah 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 blah, and they could figure out an answer. So I could say that when Richard Feynman is saying, well, when you run in the rain, more rain hits you in the face than hits you from behind, and so therefore you'd get dragged to death. Well, the argument is maybe there is a mechanism that defeats the drag. All right, now I've provided the rather simple example that you could imagine something in space, and then you could imagine I throw momentum into it. And so it's a perfect system, all right? The thing I'm throwing in, okay, never loses momentum. So once it goes in, it's just going to keep bouncing back between these two surfaces forever. And the distance of these surfaces, like with atoms, are essentially tied to each other with a spring mechanism. That is, they can move closer and further away. They have tension, so you can move them. And so the trick is now once I've thrown it in, I always throw it in one way first. So it goes from going 0 miles an hour, right, to going whatever the momentum is. So we'll just call that a 1, right? So now it's going 1 mile an hour, right? It's going forward. This thing hits, and then this little arrow reflects, right? And it's going to go back, and it's going to hit the back surface. Well, because it's moving, the back surface is now in a new position, right? So now the back surface is here, right? So this hits this surface, and it stops moving. So now it went 1 mile an hour for the time it took this line to go to here. So that time is a small time. It's a little bit less than time, right? Because this surface showed up quicker. This surface moved, therefore this arrow hit sooner, and now it's going to reverse. So now the speed stops. So we went from 1 mile an hour, and now we're going 0 again. It didn't go negative. right? It just takes away the momentum we had. And so now the arrow is going to go back this way again, all right? But the thing is, okay, this surface had moved, okay, just like this one had moved. So it's not moving while this arrow is going, so it's going to be able to hit it, but that surface is now this. All right, so this surface moved. Now this surface had moved while this one was moving. They both moved together. So by the time this arrow gets here, this surface is a little further away. So that time is going to be regular time. You know, it's the same distance. This arrow always is the same distance. This arrow is the one that gets shorter. So anyway, it shows up at this surface and goes 0 again. I mean, it gives it 1 mile an hour again. So now it's going 1 mile an hour again. So it goes between not moving, right? And then it stops, and then it moves, and then it stops, and then it moves, and then it stops. Now the trick is, that would work. You're saying, okay, I can see how something could have velocity forever because there's no negative in there. All I put in there was a positive motion in one direction. It stops, and then it goes again, and then it stops, and then it goes again. So it will work. It will keep going. But the trick is, right, is as it's moving, it's coming into more force this way. So there is force going this way. So it's just a fact that the universe contains this equal amount of force, let's say. So the trick is now, though, now let's figure out what this force is doing, right? I mean, because it's moving, this force is always hitting a target that's moving away from it, right? It's either stationary or moving away. And this one's hitting a target that's either stationary or always moving towards it. And so the trick is going to be is that, you know, there's going to be a resistance to this motion, because as it moves into the force, it's essentially making more force. That means it's going to have something fighting against it, forcing the reflection. And that's what we're really talking about. It's when will the reflection happen. So as it pushes against this, it causes the reflection to happen sooner, which compresses the box. So now the box is getting compressed because you're not going as far with this surface as you go with this surface. So this surface keeps moving the same amount. You know, nothing changes. It's the right word for it is think of a way to say it. Well, anyway, we'll just say that this surface is going to be affected because it's moving into a force. This surface isn't going to be affected because it's moving away from a force, and you're not going to know the difference. It's not exactly the right way to say it. But anyway, so just understand. So this surface starts to move more than this surface moves away. And that means the box compresses in size. Well, if the box compresses in size, that means these arrows start moving theoretically. They appear to move much faster. That is, they have interactions with the surface at a higher rate. And the higher rate they have interactions is real energy. So the closer these two surfaces get to each other, right, the faster these interactions are taking place. And that means with interactions equals the same thing as an arrow. So as I increase the number of interactions, I'm theoretically increasing the number of arrows that are hitting the surface, that are pushing against the force. So as this surface moves towards that surface, there's more energy pushing back because you've made the time, the amount of time it takes for the arrow to go back and forth, shorter. And so in the same amount of time, you'll have more arrows hitting this surface than are hitting you from the external world. So all the thing has to do is the machine, all it has to do is keep contracting proportional to the energy coming from the external world. So if the box can keep getting smaller as it's going faster into more density, it just has to have, and there just has to be an equality, really. So once you establish something's velocity, like a material wrench in space, or throw it into space, what's really happening is while you're throwing that wrench, these surfaces are being established as being a certain distance apart. And by making it a certain distance apart, I'm creating a certain amount of energy trapped between them. So the simple argument would be you could understand two ping pong paddles. I'd use that example. But if there's energy trapped just bouncing back and forth between two things and it runs at a constant speed, you can sort of just understand that the closer I bring them together, the more energy is going to be pushing them apart. Right? So the closer I bring these two together, there's going to be a higher pressure in between them, and there's going to be more of a motivation to move. And the trick you're doing is merely establishing that this one and this one are tied to each other, and the motivation is going to be to go that way. So they're tied to each other in such a way as that you convert this pressure into that pressure. See, is there any way to say that? Yeah, so I would argue that you can do that with 3 or 4 little protons and electrons in an arrangement, and that you'll be doing exactly that. You'll end up converting this sideways pressure, the pressure between their attractions and the pressure between their repulsions will be essentially the size of the cart. It'll make the cart smaller, and all they have to do is flip each time this energy goes back and forth. Is flip those positions, and that way it can just go, stop, go, stop, go, stop through space. And it will meet any drag that's opposing it. Alright, well that's the the essence of the theory. There's nothing theoretically impossible in the description. Again, I'm just saying it's you just have to think in terms of there's more than one thing going on, and it's not that complicated. So it's just like, the whole thing with electromagnetism, right, is really just the one point, is that yes, you can understand the interactions where things repel and reflect, and the one that's a little bit weird, and then you have ones that'll go this way, but the one that's a little weird is the one that goes into the third dimension. So the motor force, and that one is completely dictated by these circumstances about which way that force comes back, into something and creates attraction. So I guess I could do that part because this is sort of related to the simulation. The reason why the simulation has taken a while is because we're trying to simulate 3 dimensions and 2 dimensions just because it's easier. You can create more energy in a 2-dimensional simulation than you can in a 3-dimensional. Runs faster. There's lots of advantages, lots of reason to want to do that. But then you have to synthesize the 3rd dimension, and that's the part where you start to get into trouble. So the simple rule is, sort of simple, is that these objects are actually sensing each other's reality. So this object is reflecting, this stuff, and this object is reflecting from the universe this yellow stuff. The yellow stuff comes in and it just reflects perfectly. So you can sort of understand that if a yellow bit tried to go this way and it got deflected out this way, that there wouldn't be any yellow coming this way, so there couldn't be any reflections. And that even if there was a reflection, a little bit of yellow came in this way and then reflected back, it would still be doomed to leave, so it would never get caught between them. But not getting caught between them isn't enough to create attraction. So what's really happening is there's a decision to be made about which dimension the energy goes into. And so the decision is, I sort of pointed out, if you do this 3-dimensional thing, you can sort of figure out 2 dimensions are always on the same plane. So this dimension and this dimension are always on the same plane. One dimension is off the plane, and 2 dimensions are always on the same plane. So you can argue that theoretically, this right-hand turn is the same as this right-hand turn. Any one of these directions is the same from the perspective of the thing. It's coming this way, and it's saying going up is really the same as going this way. If there was no gravity, you could sort of get that. Yeah, if you're going against gravity, then it's different. But I'm just saying, if you can think of it being in space, and you have the choice up or left, there's not going to be any energy conservation argument to be made that the two could possibly make a difference. So the point is that the idea of going out this way is just an idea of going out that way. It could go out this way, it could go in that way, or it could go that way. And so which way it goes, though, is going to be dictated by how much of this stuff is hitting it. So if there's a bunch of blue stuff through, wherever the most blue stuff, let's say green, whatever. So the universe is hitting it with a certain amount of green from every direction. And the one direction it's not getting hit with green from is this direction, right? This thing isn't reflecting any of that because you're not giving it any. So it can't reflect any. So there's less coming from this direction of the green stuff. And that's going to decide when a piece of energy comes in and it's going to get diverted. Which way it gets diverted is going to be dictated by which way, well, this is the object I was talking about, so I'll use green as the example. So if a yellow thing comes in, it always reflects. Yellow always just reflects. The energy goes in, the object moves. It's always just a reflection. A hit, an absorption, which in turn is it's just exchanging. It just gives away this way, and it keeps this way. So it had an arrow going this way. It gave that to the universe, and it kept this one. So there's a 2x exchange in its momentum, in the sense that it lost a bit going that way, and it gained a bit going the opposite way. And so when this other sideways thing happens, so the decision is going to be that if there's less blue stuff hitting this surface, then when a blue thing, or green, yeah, comes in from the side, it's going to make the exchange in the in the dimension that has the least force coming in at it. So it's going to add the arrow going towards as the momentum, and it's going to give away the reflection in the opposite direction. So it'll come in this way, it'll make an exchange for this, for that, and then it'll end up moving towards the thing it'll move towards the surface that's getting hit with the least blue stuff, green stuff. So there's probably a way to illustrate that more simply, but that's the side. It's not like a right-hand rule or a left-hand rule. They say that like it's consistent. The rule is about its motion and what's causing its motion. So it's not just the fact that an electron is moving in a direction that means you're going to engage in the motor force, where you're going to create this change. The fact that it's moving in a direction means there's less force, okay, somewhere that caused that. And that's the thing that's going to be sensed by the electron. And then the electron will decide, oh, I go up instead of forward. So when I get hit with this new force, you can see that, right? Yeah. So I get hit with this new force, and the new force is going to be interpreted, okay, not just based on the fact that I'm going this way, but that I'm going that way into a field, okay, that is a specific field. And that's what decides whether it goes up or whether it just turns left or right. So it doesn't add energy automatically in a right-hand direction. The right-hand direction is dictated by actually what kind of force is hitting the electron as it's traveling, in the direction it's traveling. And if it's an absence of blue force, then you'll add energy. If there's an abundance of blue force, then it takes the alternative path. Yeah. All right. Now let's see if there's anything else worth explaining. All right. I guess I'll just summarize 2 + 2 + 2 physics. Just point out again. So all there really is, and this, like I said, gravity is just depolarized charge. But anyway, so it's not really an electric universe. It's a non-polarized universe. Well, anyway, so there's just two things, two kinds of force in the universe and two kinds of matter. Well, that's not a very good way to do two kinds. So you have these electron things and you have the proton things. You have plus and minus charge objects. And then you have a force, the little bits. All right, well, I mean, what's the point of drawing them this small? But anyway. And they're the things that give these bits momentum, move them. But they have to keep hitting it. So the idea is so say when they move an electron through an accelerator, what's really happening, I think, is there's a bunch. See, they're really creating like very long X-rays and gamma rays. So there, you can think of it as like a really long photon. So they're creating a piece of energy that has a really long ray length. Okay, so it's a pulse. I mean, it only lasts a 1/1,000,000th of a second. Well, in 1/1,000,000th of a second, right? If I was to fill the distance that force travels in 1/1,000,000th of a second with an X-ray, that is a ray of X-rays where they're very, very close together, the little bits of force, you can understand 1/1,000,000th of a second at the speed of light can be 20 meters, right? Who knows what it is exactly, but it could be a pretty big distance, right? In 1/1,000,000th of a second, a photon goes pretty far, all right? So anyway, so depending on how long that pulse is, the pulse will say how far you can push the electron. But what's really happening is that the electron is being pushed by a constant barrage of bullets. There's a bunch of bullets that just keep hitting it, and keep hitting it, and keep hitting it, and that's what's moving it. And as soon as those bullets run out, that is, this pulse goes through the electron and is causing it to, it doesn't really go through the perpendicular way, so I don't want to confuse you. It goes through the electron. You can just sort of, it gets shorter and shorter and shorter as it goes through. But it won't run out for 15 or 20 meters. And then the electron will stop moving. So if you make your pulse shorter than the length of your accelerator, I guess I would argue the electron stops moving. The electron won't get to the target. So the pulse always has to be long enough to create a long enough ray to keep pushing the electron. But anyway, so the basic idea is you have two kinds of force, two kinds of matter, 2 plus 2, and then you only have these the simple argument. You really have three kinds of interaction, but we're just saying for the sake of, the sake of argument, that the basic idea is that you have two kinds of interaction, which is you have the reflection, a perfect reflection, that is a perfect exchange. This goes inside, this leaves. Okay, this way leaves, this way stays. Or you have the interaction where it goes in this way and the momentum is exchanged this way, gains momentum this way, and the force leaves this way. So it's this perpendicular thing, and that's it. That's all you really need. Now obviously there's this third interaction where it goes in and out of the board because there's 3 dimensions. So it's 2 plus 2 plus 3, technically. But I'm arguing that, yes, this simple method, this travels the speed of light, this has 0 speed, and the only way you give these things speed is to hit them with extra pressure. You have to keep pushing them along. They won't just fly on their own, so to speak. I think that's inevitably going to be the fact. And that it's only when you arrange these that you create something solid that can maintain its velocity through space by creating a wind engine, a sail position that allows it to capture the wind blowing sideways. The sideways winds are blowing. See, imagine what you could do with a sailboat if wind could actually blow in both directions. From one side it's blowing this way, from the other side it's blowing this way. Then you could just make yourself a V sail and you'd have it made, right? Because all the wind would go this way, the reflection, and all the momentum would go this way. And you could build up quite a bit of speed that way because there's no limitation. The wind is going to be here too. The wind's going to be here. So no matter how forward you go of it, you're not running away from the force that's pushing you. I suppose that's a really important thing to emphasize, that you're not running away from the force that's pushing you. You're not outrunning the bullets. So the idea is, let's use bullets because that always makes it, that helps. So, you know if you were pushing something by pushing this way, okay, that this speed, as soon as this thing starts going, if this is going 10 miles an hour, and as soon as this starts going 10 miles an hour, it can't gain any momentum from the wind anymore, the force. Just can't gain anything because it's outrunning the force. The force never moves to here because this keeps moving away from it. But if the wind is coming this way and the wind is coming this way, you can sort of understand that no matter where I go, I'm going to run into more wind. All right? So I can move and I'm still getting hit by this 10 mile an hour wind. Now, I'm going to convert that into 5 miles an hour momentum. All right, but the point is that I can keep capturing more and more 5 mile an hour wind. So I get half as much energy, but I get it constantly. I mean, every foot I'm getting a new piece of wind, 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 a new piece of wind. So I could really zoom, but that's what sailboats are doing, right? So just cut this example. Instead of having the wind blow both ways, just understand that, yeah, this is the sail on the boat. The boat is here, and all it's doing is taking advantage of the fact that if I have a wind coming from the side, I can maintain motion in this direction and gain more and more speed because I'm not limited by the fact that I'm outrunning the force. I'm not outrunning the force here. I keep plowing into new force, new force, new force. And that's the trick that overcomes drag. Okay, I think that's enough of a video. So, yeah, till the next time and such, so forth and whatnot.